look at the second half of this review sheet. So Keno is a game that's in the casinos. It's basically you sit around and you mark a card, you mark a number, they pick 20 balls, and so basically the probability you win is 20 out of 8 or 0.25. So well, look, what's the payoff distribution? If you win $3. Right? So you could either win, so if X is your payoff, you're either going to win, X you take on the values 0 or 3. So you're either going to win $0 or $3. So the probability that you win those $3 is 0.25, which means the probability you lose is 75%. So for B, wasn't the mean payoff? Just, again, you could put that in the calculator or just realize it's really just doing 3 times 0.25. So the expected payout is 0.75. Now the standard deviation, that probably, that would require you to go into the um, calculator, but we're not asked for it here, so we'll just keep moving forward. So in the long run, how much does the casino keep from each dollar bet? Well, if the mean payout is, right, so the mean payout is 75 cents, you pay $1 to play, which means the casino keeps 25 cents per play. All right, for these two questions, just figure out what are we looking at. Is it binomial or geometric? So we don't have to solve it. So the probability a student passes a written test for their private pilot's license is 0.75. What's the probability a student will fail the test on the first and pass the second? In other words, what's the probability that their first pass is on the second attempt? This is until success. So this is geometric. Out of students aged 16 to 18 with A or B averages, 78% cheated to get higher grades. 10 randomly selected students, so n equals 10, so probability 0.78. Two outcomes, they either cheated or they didn't. Each student is independent, and we got a set number of trials, so number 7 would actually be binomial. Number 8, just using this chart. So this is kind of like the watermelon problem, except we don't have to fill in the chart ourselves. It's already filled out for us. So A, we're just adding a constant. So the expected value of x plus 50. So this one, you would just do 50 and another 50. That's 100. And the standard deviation of x plus 50, since we're just adding a constant, it doesn't affect the standard deviation, so it's still 8. All right, so now we're going to multiply by a constant. And if you multiply by a constant, you multiply both by a constant. See, now all of a sudden we're going to combine a random variable. What I might do here, since we're going to have that 0.5y, maybe we do a second little section, so 50 and 3, another section for my chart where we calculate the 0.5y. So now we want the expected value of x plus 0.5y, and so that's just 50 plus 50, which is 100. And then the standard deviation of x plus 0.5y. So we need to do 8 squared plus 3 squared. So 64 plus 9, take the square root of that, is approximately 8.54 for D, x minus y. So that's just 50 minus 100, which is negative 50. And for standard deviation of x minus y, even though we're subtracting, we have two random variables, right? We're combining x and y. We're still going to use variance, and you're still going to add. So 8 squared plus 6 squared, and that's going to give us 10. And finally, e x1 plus x2. This is just like doing x twice. So the expected value of x1 plus x2, you just take 50, add 50, so that's 100. And then the standard deviation of x1 plus x2, we have to use variance because we're combining random variables. So 8 squared plus 8 squared. And if you take the square root of that, that's 11.31. All right, and then finally, number 9, preemies, babies born more than 3 weeks early. 10% of all live births are premature. So suppose 250 live births are randomly selected, and the number of X, number of preemies out of 250. Can we use a normal approximation? So in other words, our NP and NQ greater than or equal to 10. So here, N is 250, P is 0.10, so 250 times 0.10 equals 25. That's greater than or equal to 10. And then 250 times q, which is 1 minus p, 0.9, is 225. And that also, excuse me, 225, and that's also greater than or equal to 10. So yes, a normal approximation can be used. So let's do that. So for part B, what's the probability that x is between 15 and 30? So what we need to do, calculate two quick z-scores. So z1 equals 15. Mean the standard deviation. If we're to finish this off, and z2 is going to be 30 minus the mean over the standard deviation. So the mean, keep in mind, is just n, 250 times p, 0.10, which is 25. So I can go ahead and fill those two values in. That also tells me that my curve is centered at 25. And our standard deviation, remember, is n times p times q. And you're going to take the square root of that. And that's 4.74. Alright, so my first z-score is negative 2.1, if I could read my calculator correctly. And then my second z-score is 1.05. So negative 2.1 up to just over 1 standard deviation. We could use a normal CDF at this point. So that's going to put us at 15 up to 30. The mean is at 25. So that probability 0.84. Remember to write your answer in context. And then what's the probability there are fewer than 20? So one more time here. C is the probability that x is below 20. So the z-score here, 20 minus 25 over 4.74. I'm still using my mean and standard deviation from above. Negative 1.05. Draw a quick curve, centered at 25. 20 is just below 1 standard deviation, shading this way. So here we go, normal CDF from negative infinity up to 20 with a mean of 25 and a standard deviation of 4.74. So negative infinity up to 20, mean of 25, 4.74. So it should be just under 16%, and sure enough, that's 0.146. Make sure you write your answer in context. A couple other problems real quick, just to remind you about using your binomial formula. Probability that we get an naughty child, 0.25 equals 15. We want 5 out of 15, and just using your formula, that answer right here, 10, choose 4, and then you get the probability, the number of naughty, and this is the probability of naughty, and then probability not naughty times raised to the not naughty. And then remember, make sure you can remember, is it binomial? So you want a fixed number of trials, right? Fixed number of trials. You want a fixed probability. You want each trial to be independent. And you want 2 outcomes. The only difference for geometric is you're going until success. But you still have a fixed probability, you still have independence, and then you still have 2 outcomes. And the other thing to make sure you're aware of, you can't use a normal approximation, where NP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. Either one of those will work.